Hi, let's talk about atomic spectra and how it affects the Big Bang and the atom. So, first question, how is the absorption and emission of atomic spectra evidence that supports the theory behind electrons having discrete energy levels? Well, we've been exploring about quantum energy and quantum levels and all of those things, and now we're going to look at the theory and how this relates to atomic spectra. So, when we think about atomic spectra, think of when you light something on fire, and it may not necessarily be like an orange, especially for different elements, they're going to come in different colors. So, when atoms absorb energy, so when you're lighting things on fire, or when you're fusing them in the sun, or you're basically giving different types of energy to electrons or elements, the atoms absorb that energy and their electrons move to a higher energy level, denoted here as E2. Then, when those electrons lose that energy that it was provided, it moves back to its original lower level, and that move from higher energy to lower energies produces this light spectra that we can visualize. And the light spectra is the release of energy in terms of light. So some of the evidence is that every element has its own very specific atomic emission spectrum, and energy is only absorbed at or emitted for different atoms and elements at specific energies. So frequencies and wavelengths correspond to colors, which then correspond to elements. And so you can look at the emission spectrum of these different elements. And if you're wondering why sometimes there's different colors, it's because we have isotopes, and isotopes have different energy requirements, even though that has the same amount of electrons. And sometimes we have ions, which have different amount of electrons in correlation, and those different electrons and ions, well, we treat them kind of as cousins, or they're the same element, but they're going to have different emission spectrums. So, how do we use this data to determine the elements that make up a star? How do we use this emission data to determine elements in our own universe? All of that fun things. And so the first thing you have to understand is oftentimes you have to go beyond the atmosphere in order to get a clear spectral picture of stars and other items, because the atmosphere has its own color, and it does absorb some wavelengths, so it may not always be clear going through the atmosphere. So you go above the atmosphere, and then so we use telescopes in space to determine the absorption spectra of the sun and other stars. We often do stars far away. We look at other planets and other universes and other galaxies, and the absorption spectra are unique to each element. And so you can basically determine the colors and the color frequencies, and that match them like a fingerprint, allowing for identification. And you can kind of go on here. So if you're looking at the sun spectral lines versus wavelength, you can see that oxygen has a much higher wavelength, that calcium has a very small wavelength, and those wavelengths and frequencies then relate to the colors that are released. So we can match colors, which then relate to a wavelength, which then relate to a specific element, and this is how you match items and then elements. And then, well, we can do that in space, but can we do this here? And yes, we can, because almost every color you see is not what is being absorbed, it is what's being reflected. So if you're looking at something that is red, it absorbs every other color, and red is the only one not absorbed. It's reflected. So you're not really seeing the color that items absorb, you are seeing the color that items do not absorb. And everyone's always curious about how electrons are related to lightning and static electricity. And both of these items are electrons going from an item of a place of high buildup to a place of low buildup in the form of static electricity. It's often just a little shock and lightning. There's a lot more electrons, and so it can be a much bigger zap